Hello and welcome to another Common Core Geometry video by eMathInstruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson number 5 on Similarity Criteria. Wow, that sounds exciting. So let me just kind of lay it out for you, right? Similarity criteria is the idea that we don't need to know that all of the sides, all the corresponding pairs of sides in similar triangles are proportional to one another and all the angles are equal in order to know that two triangles are similar. There are going to be simplified sets of criteria that will allow us to say, yeah, those two triangles are similar to one another. All right? And that may sound a little bit, well, similar to what we had with congruence. And speaking of which, let's kind of talk about that a little bit, right? Remember the congruence criteria? Right, when two triangles are congruent, all the corresponding sides are the same length, and all the corresponding angles are the same measure. And yet, we had all these different theorems. Side, 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 angle, side, angle, side, angle, angle, side, hypotenuse, leg, angle, side, angle. Lost that one a little bit in the light. Right, we had these 5 criteria that said you don't need to know everything is equal about these two triangles. If 3 sides are congruent to 3 sides, they're congruent. If a side, an angle, and then another side are congruent, they're congruent, etc. Right? We're going to have the same thing for similarity, except pared down a little bit. Thankfully, there's not going to be quite as many. And today what we're going to do is we're going to figure out those similarity criteria and why they work. So let's jump into it. All right, exercise number 1. Given triangle ABC and triangle DEF with angle A congruent to angle D and angle B congruent to angle E, do the following. Letter A. Give a dilation of triangle ABC centered at A that would make the image of AB, just AB, don't worry about anything else, congruent to DE. Be as specific as possible. All right? This should be pretty easy. Why don't you pause the video and go ahead and do that. All right, well, let's talk about it. They already gave us the center, but let's just talk about it again. Ooh, I've got that nice thick black line going on here. Let me change it down to something that's a little bit easier. Well, we're going to have our center at A with a dilation constant or a scaling constant, whatever you want to call it, of K equals, now remember, we always want to do the new length divided by the old length. And because all we want to do is make the image of AB congruent to the image of DE, then I'm just going to say I have a scaling factor of DE divided by AB. That's it. DE divided by AB. Okay, so now imagine this, right? I've taken this triangle, I've dilated the entire triangle with a center of A, all right, and I've dilated it in a way that guarantees now the new length of A prime B prime is the same as the length of DE. That's what I've done in letter A. Would this dilation change the measure of angle A or the measure of angle B? Explain. All right, the answer is no. No. Why? Dilations are angle preserving. All right, so in this new triangle, right, in this new triangle, whatever it is, right, this new triangle that's C prime, A prime, B prime, right, we would know these two angles were still the same, and because of the dilation constant we've chosen, we would now know, that should only be one mark, that those two side lengths are the same length. And that leads us into C. Why would triangle A prime, B prime, C prime, this thing, now be congruent to triangle DEF? What would allow us to say that those two triangles are congruent? It would be the angle, side angle theorem of congruence. And the only reason I'm tossing in this of congruence piece here is because I want to now distinguish similarity criteria from congruence criteria. Now this is remarkable, right? Think about the technical definition of similarity. The technical definition of similarity was that there would be a similarity transformation, right, that includes a dilation, that would cause one of the triangles then to be congruent to the other. So think about this now, right? If we've got a situation where we've got two angles of one triangle congruent to two angles of the other triangle, then all we would have to do is dilate this triangle by a factor that makes the length between the two known angles to be the same, and then these two must be congruent to another, which means these two have to be similar to one another. If simply two angles of this triangle are congruent to two angles of this triangle, then we can easily come up with a dilation that makes the two triangles congruent to each other based on angle side angle, and therefore these two have to be similar. All right, we don't even have to make this triangle lie on top of this triangle, simply making these two triangles congruent. And that brings us to the absolutely most important criteria for similarity, the angle-angle criteria. All right, now we know if two triangles are similar, you really have angle-angle-angle. These two angles are equal, these two angles are equal, these two angles are equal. But simply if we know that two pairs of angles of one triangle are equal to two pairs in this triangle, then the two triangles must be similar. And again, the reason is really cool, because we could take either one of these triangles and dilate them by the ratio of this side length to this side length, and that will cause the two triangles then to be congruent. But even if you don't know all of that or quite understand all of that, the thing that's very important is that if two angles of one triangle are congruent to two angles of another triangle, those triangles must be similar. Only for triangles, not for anything else. All right? Undoubtedly the most important of the criteria. So let's take a look at this and see how it pans out. Exercise number 2. In the diagram shown, QR is parallel to NP. Prove that MQR is similar to MNP. All right? So I want to prove that this smaller triangle, MQR, is similar to this larger triangle, MNP. Okay? Now, let's just kind of work through this together and see how the angle-angle similarity theorem works. Okay? In a certain sense, one of the things that's tricky about the angle-angle similarity theorem is oftentimes you can do a bunch of different things with it. So, for instance, one thing I could do is I could label these angles 1, 2, and these angles 3, 4. Okay? And I could say that angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4. Actually, let me just do this. Now, why can I say that 1 is congruent to 2 and 3 is congruent to 4? Well, I could say that because they are corresponding angles created by parallel lines. All right, but that's enough, right? Because now I can say that triangle MQR is similar to triangle MNP by angle-angle theorem of similarity. Now, most of the time, we're just going to say by angle-angle. All right? I just want to kind of keep track of the difference between similarity criteria and congruence criteria. Now, you wouldn't have to use these two and these two. There's actually one other angle that we also know is the same between the two triangles, and that's actually the shared angle M. All right? But I need to have two pairs. So either 1 congruent to 2 and 3 congruent to 4, or 1 congruent to 2 and maybe M congruent to M by the reflexive property. All right. So that smaller triangle congruent to that larger one. And again, we're going to see this picture time and time again where we sort of have a triangle embedded within another triangle and two sides being parallel to one another. We saw that as early actually as unit number, I think it was 4. All right, but let's keep going. Exercise number 3. If in the above diagram MQ is 8, NQ is 6, NP is 21, then what is the length of QR? We've already talked about this a little bit, but it's really, really important that when you're working with two similar triangles to maybe draw the pictures of the two triangles separately. So for instance, I'm going to draw MQR like this, and then I'm going to draw the larger one, MNP, as being the same shape but slightly larger. This now allows me to kind of not see that double line here and just be able to say, well, MQ is 8, NQ is 6, but that means that MN would be 14, right? Maybe I'll do the numbers here as well. NQ is 6, and NP, let's see, is 21. And I want to know the length of QR, right? I want to know this length. Okay? Now, what's kind of nice about this is that we can very easily say the following. Remember, it's all about these kind of like ratios or proportions of corresponding sides. I can say, well, maybe I'll call this x so that we really kind of set up an equation. I can say that if I took x and I divided it by 21, if I took this length and I divided it by that length, I would have to get the same as if I did 8 and I divided it by 14. Okay? Smaller divided by larger equals smaller divided by larger. In two similar triangles or two similar figures in general, the ratio of corresponding sides is proportional, meaning that you can say this divided by this equals this divided by this equals this divided by this. Now, of course, we can solve this by just doing a little bit of cross multiplying. I would get 14x is equal to 8 times 21. All right, is 168. Then, of course, I could divide both sides by 14. That's easy enough even on this calculator. And I get x is 12. Let me move this out of the way. And there we have it. Okay? That's something that we're going to do a lot with similarity. All right, we know various sides of two similar figures, typically triangles. We look at one that we're missing, and then we just set up that proportion, right? This divided by this equals this divided by this. The most dangerous thing here is when people do something like this. They do something like, well, x divided by 21, and then they stick over here and they say equals 14 divided by 8. Right, so they'll do this divided by this equals this divided by this. Now, small divided by large equals small divided by large. Okay, let's get rid of that. Let me kind of step out of the way, give you a little bit of time to think about that, and then we'll move on and do another problem. All right, let's do it. Advance. Okay, now, by far, no question about it, the two, let me just put that right in the way, the most important similarity criteria is angle, angle. But there are two other ones, just two more, right? There are 5 congruence ones. There are just really 3 similarity ones. And these are the other 2. One of them is what's known as the side, side, side criteria. So if we have 3 pairs of corresponding sides of 2 triangles are proportional, then the 2 triangles are similar. Even if we know nothing about their angles whatsoever, if I look at these 2 triangles, I can say, oh, 15 divided by 5 equals 12 divided by 4 equals 24 divided by 8. Okay? So in other words, this divided by this is 3, this divided by this is 3, and this divided by this is 3. Okay, if that keeps being the same number all the way along, then the 2 triangles must be similar. The other one, and don't get me wrong, right? Couldn't that be confused with side, side, side for congruence? Now we have side, side, side for similarity, but the sides aren't equal, they're proportional. And then we have side, angle, side. if two pairs of sides, not three, if two pairs of sides of two triangles are proportional, and the angles included between the proportional pairs are congruent, not proportional, but congruent, then the two triangles are similar. So again, let's take a look at this sort of scenario. Same kind of idea here. We've got two pairs of sides. Notice again, I'm sticking with that 3. 15 divided by 5 is 3, right? And 12 divided by 4 is 3. So now I have these two pairs of sides that are proportional. This divided by this equals this divided by this. And the angle in between them is equal, right? Not proportional. This angle can't be 3 times that angle. It would be 300 degrees. What would that even mean in a triangle? Yeah, couldn't happen. All right. So what we definitely want to do is make sure, though, that you understand why those two criteria exist for similarity. And again, it goes back to the technical definition of similarity. The similarity criteria states that if there's a dilation of one figure that will make it congruent to the other figure, then the two figures must be similar to one another. All right, we don't even have to go ahead with mapping one figure on top of another. If we can just show that, hey, I dilated this particular triangle with this center and with this dilation factor, right? And now the two figures are congruent to one another, then the original two figures had to be similar. Let's get at that in exercise number 4. Say that you have the following diagrams with only the information marked. In both cases, give a dilation with a center and a factor that would map triangle ABC onto an image of A prime, B prime, C prime that is congruent to DEF. All right. So here, right, we've got a side-side-side scenario. All right. What dilation of triangle ABC would make it congruent to triangle DEF, and why? All right, well, let's talk about it. First, the center could be anywhere. It could be absolutely anywhere. All right, that doesn't matter. With a scale factor of k equals, well, 2, right? K equals 2. You know, and when we do that, you know, so let's say at A. Let's say it could be anywhere, but we put it at A. You know, what's going to happen, obviously, is it's going to stretch out. So it's now going to look like this. This would then be 6. This would be 10. And this would be 8. And of course, now triangle A prime, B prime, C prime will be congruent to triangle DEF for one very simple reason, right? Triangle A prime, B prime, C prime will be congruent to triangle DEF by the side-side-side theorem of congruence. All right? So the side-side-side theorem for similarity comes from the side-side-side theorem for congruence, along with the definition of similarity being that, all right, we got a dilation that turns this triangle into one that's congruent to that triangle. All right? Let's take a look at letter B. All right, here we've got a side angle side situation. Again, 15 to 10, 21 to 14, and then that 120 degree angle between the two. So again, pick yourself a center. This time the dilation factor is a little bit trickier, but I'm sure you can figure it out, and then let's talk about it. All right, let's go ahead. Again, the center could be anywhere. But let's pick, I'm going to pick point B. Point B. It almost looks like the word point B. Okay? But what's the K going to be? Remember, we want to make ABC congruent to DEF. All right? So we should take one of the newer measurements and divide it by one of the older measurements. So maybe we'll take that 15 and divide it by 10. And that will give us either 3/2 or 1.5 as the scaling constant. And again, what's going to happen is this is now going to stretch out to here. This would now stretch out to here. All right. This would now be 15. This would now be 21. And to verify, by the way, 21 divided by 14, if I divide both by 7, would give me 3/2, which is 1.5. Same ratio, right? And now, triangle A prime, B prime, C prime would be congruent to triangle DEF by side angle side of congruence. All right. Now again, these two are important to know. You're supposed to know that, all right, two triangles can be proved similar either by angle-angle, or side-side-side, or side-angle-side. Angle-angle, we'll see, is used way more often than any of the other criteria. But it is kind of interesting because these other two, side-side-side and side-angle-side, come from a combination of congruence theorems, sort of using the same letters, if you will, and also the technical definition of similarity, which is that there's a dilation that will stretch out this one triangle so that it becomes congruent to this other one. All right. Strangely enough, there aren't things like angle-angle side or hypotenuse leg or whatnot for similarity. Just the three: angle-angle, side-side-side, and side-angle-side. So let's see how this plays out in one more problem. Okay. Now this one can be quite challenging, both to teach and to just solve for itself. All right. But it's very typical of a standardized exam. And the irony of it being hard is that it's a multiple choice problem, which we typically think of as being kind of easier than free response. But let's take a look. Exercise 5, it says in the diagram below, which of the following information would not be sufficient? Not be sufficient to show that ABC is similar to RST. That ABC is similar to RST. And I might have to do some work with like different colored pens and things like that because it's kind of nice. So let's take a look at choice 1. Okay, choice 1 says, well, if I do RS divided by AB, that's equal to ST divided by BC. That's equal to TR divided by CA. And notice in each case what I did was I took a side length of RST and I divided by a side length of ABC. So this is actually the side-side-side theorem of similarity. So that one's good. No problem there. Okay, so that's going to get the job done. The ratio of all three corresponding pairs of sides is congruent. All right, let's look at the next one. All right, AB divided by RS is equal to AC divided by RT, and the measure of angle A is congruent to the measure of angle R. All right, well, that would be the side-angle-side theorem of similarity. All right, in other words, I take this side, I divide it by that one, I take this side, I divide it by that one, and then the angle between the two corresponding sides is equal, and therefore side-angle-side similarity theorem. Erase. All right, measure of angle S is equal to the measure of angle B, and measure of angle C is equal to the measure of angle T. That one's the easiest one of all. That's the angle-angle theorem. So almost by process of elimination, it's got to be choice 4. And yet the weird thing about choice 4 is if you look at choice 4 and you look at choice 2, they look awfully similar to one another. So why is choice 2 an okay way to prove the two triangles are similar, but choice 4 isn't? Let's take a look at that one in some detail. Maybe here I'll need to erase a little bit longer. Anyway, so let's take a look. Here I'm going to say RT divided by AC, oh, that's good, is equal to TS divided by CB, no problem there, and measure of angle B is equal to the measure of angle S. All right, that sure looks a lot like choice 2. It sure looks like side angle side, but it's not. And it's not because the angle that's equal is not included between the two sides, right, or the two pairs of sides that are proportional to each other. Side angle side has to have the angle come between the two sides, or two pairs of sides, that are proportional to each other. So in fact, choice 4 is the one that's not enough. All right. Now, of course, where we're going to eventually go with this is eventually use all three criteria, primarily angle, angle, in order to prove that triangles are congruent. For now, let's just wrap it up. Okay. So, when two triangles, or any two figures, are similar, all their angles are equal, and all corresponding side pairs are proportional to one another. But we don't need to know all of that in order to conclude that two triangles are similar to one another. What we saw today was that there are three primary criteria: two pairs of angles congruent to each other, or all three side pairs, all corresponding side pairs proportional to one another, or two pairs of sides proportional to one another and the angle in between them being equal. All those will allow us to conclude that one triangle is the same shape, but not necessarily the same size as another triangle. All right, thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.